Let's get to integration technique, section 8.1. So, well, that's something covered roughly back in Calc 1. However, in this section, we're going to extend these techniques that we use for integration. So, the idea is that you will be given an integral for which, well, by just looking at it, we wouldn't be able to compute it just right away using a regular U substitution. Yes, we'll do that U substitution later. First, we need to do some algebra on the integrand, and this first page gives us a really good summary of all the different techniques that we can apply on an integrand. Alright, so number one, well, sometimes we have powers of binomials, trinomials. Well, a good first step is to, in this case, to expand the numerator, have more terms, and then integrate each term. Right, so that's one of the techniques. The other technique is to split the numerator. All right, because in this case we have a rational expression with a sum or difference in the numerator. That means in this case, like the example that we have here, we can split that into two terms, and that's because, well, that's because of the property A plus or minus B over C. This is the same as A over C plus or minus B over C. We can always split the numerator into two different fractions. Another very common technique that we need to be very fluent with is completing the square. So, and that goes whether for just a denominator with a potential completing the square that we may have, or under a radical. And this for sure is going to lead to what we did on day one on inverse trigonometric functions, integrals that the result it's an arc sine, arc cosine, arc tangent, well, you name it, right? Another one, well, that's when we have polynomial over polynomial, and that's when the degree of the numerator is greater than or equal to that on the denominator. In that case, well, let me write that as a note here. So that's important. That's an important note here. Degree of the numerator is greater than or equal the degree in the denominator. Whenever that's the case, polynomial long division it has to be done first. All right, and then from there we would be able to do any U substitution that could lead, well, an ln or arc sine, arc tan, arc cosine, well, depending on what we have. All right, another very useful trick right here is when we do the du part of the problem, sometimes the du part is missing a numerical term. Well, so in that case, it works to add that numerical value in order to compensate, so the u du works in this case, and we will be able to do the U substitution. Of course, we're going to do a few examples of each. Using trigonometric identities. Well, for this section, I don't think we're going to do a lot of this, but of course, we're going to get into this a lot more in depth when we go to section 8.3, I believe it is, trigonometric integration, where every single trigonometric identity will come back. We're going to use it, apply it here and there. Another very common technique is to multiply by a trigonometric conjugate. This one we're going to do one, but of course that one will be useful a lot when we get to section 8.3 in trigonometric integration. All right. Okay, so let's have a look at this integral example 1. So what do we have? The integral for x plus 1 divided by x squared plus 9. Of course, if we try to do, like a U substitution, right? So right away, u equals x squared plus 9, and du equals to x dx. Well, we have the 2x dx, except for the numerator, there's one term missing, that is the plus 1. Well, so in this case, we cannot use the u substitution just yet. We need to do something on the integral first in order to get this integral evaluated. All right, so okay, let's do, okay, any ideas on what to do for this integral? Yes.
I think it's add and subtract terms in the numerator.
Adding, subtract terms in the numerator. Okay, so what number or what quantity can we add and subtract in this case? Okay, Adrian, you have what number do we subtract? Or
also say separate the numerator.
Separate the numerator, so split this into two problems. All right, let's have a look at that. So that's the integral for x over x squared plus 9 plus 1 over x squared plus 9 with respect x. And then from here, let's split it into two integrals for x squared plus 9 dx. The integral from, oh, not from, it's actually x squared plus 9 dx. And then from here we can separately look at a u substitution, the u du part. I think this time it will work. All right, however, there's something I would like to do, so I'm going to take this 4 outside of the integral instead. That way the u du part, it's a lot easy to get in this case. All right, so in this case, let's have our u. Let me do the u sub. Okay, let me do it here. U equals to x squared plus 9, and the du equals to x dx, where x dx equals to 1/2 du. All right. So from here we will make the u substitution here, but okay, let's look at the second integral before doing the substitution. Trigonometric substitution. Well, even though trigonometric substitution works with a trick, we haven't gotten yet to trigonometric substitution. So the arctangent rule, right? The integral whose the integral of function, it's an arctan. That is, in this case, let me do another u, which is just x, du, which is dx, simply dx, and a, which is the number whose square in this case is 9, and that's 3. All right. So in this case, we're gonna need a couple of formulas. Okay, let me write that down at the top. So that's the integral of du u squared plus a squared. That's 1 over a arctan of u over a plus c. So that's one of the formulas that we will require. All right, the R10 rule. All right, so in this case, our a is the number 3 and our u is simply x. So let's do the u substitution here. So I would like to rewrite this in the following way. So this is 4 times the integral of x dx times 1/2 of, in this case, simply u. Oh, never mind, that's supposed to be the u. So du over u. But instead, this 1/2 right here, I'm going to multiply outside. I think that's easier to get all the constants in front of the integral, outside of the integral. And in this case, plus the integral of u squared plus 3 squared, which is our a, du. And this is going to give us 4 over 2, that's a 2. And the integral of du over u, what's that integral? Log ln. Ln of, in this case, x squared plus 9 And then, okay, I'm going to leave it like this for a second. And then over here, that's going to be plus 1 over a. That's 1/3 arctangent of u over a plus c. Well, one thing to recall. Number one, recall that the natural log function needs absolute value bars here. All right. However, in this particular case, because if you look at argument of this natural log function, it's x squared plus 9. That quantity will never output a negative value, will always be positive, so parentheses are fine for this one. All right, and that's something that that you might to be careful when you're working on the MyMathLab homework. In some cases, you might be required to put those absolute value bars. In some cases, MyMathLab takes it either way, like this case. All right. So that's our first example of an integral that requires a little bit of algebra before we can compute. Let's look at the next example. So what do we have? Okay, so in this case, the integral of 1 over 5 plus 3e to the x. All right, so we have a quantity in a denominator. So when I look at something like this, it seems like the form du over u, which eventually might be the ln of u form. So, okay, let's give it a try. Let's give it a try to this. And so u equals to 5 plus 3e to the x du equals 3e to the x dx. But there is a problem here. On the integrand, we're lacking that 3e to the x multiplying the dx. So in this case, we cannot just do this U substitution just yet. So, okay. Yes, this will be useful later. Let me erase it for now. All right, so what's the trick here? Here when, yes, Adrian?
Convenient one. Convenient one.
A convenient version of 1, all right? So a special version of 1. So what quantity would be great to?
5 plus 3x into the x.
Okay, do you mean like a conjugate or something?
Oh, I mean, 5 minus 3 into the x.
I'm not sure if this is gonna work. I haven't tried that. However, I have something a lot more simpler. That's when this is always gonna work whenever we have a sum or difference that involves an exponential function. So let me go ahead and show you what to do in this case. 5 plus 3e to the x. So in this case, that convenient version of 1 will be e to the negative x, e to the negative x. All right? So I'm going to multiply across numerator and denominator, see what we're going to get. So this is going to be the integral of e to the negative x divided by 5e to the negative x. And what's the product of e to the x and negative x, e to the negative x? Well, that's going to be just 3, right? So plus 3 dx. All right, so what happened here? Well, let me show a few more details. Multiply, distribute, but over here in particular, 3e to the x times e to the negative x. Well, that's 3e to the x minus x, which is 3e to the 0, which is 3 times 1, which is just 3. All right, so that's one way to see it. The other way to see this one is 3e to the negative e to the x times e to the negative x. This is the same as saying 3e to the x over e to the x. This cancels, and that's just going to give us the 3. Different ways to see the same idea. All right? Keep the one that you feel more comfortable with. All right, so I believe in this case the u du is going to work a lot better than last time because, well, The derivative of the exponential right here, 5 e to the negative x, will involve itself that e to the negative x, which actually is now multiplying with the dx, isn't it? So let's go ahead and do that. So u equals, I'm going to write this in this form, never mind. 5 plus 3 e to the x, actually, nope, that was not supposed to be. Yeah. So u equals to 5 e to the negative x plus 3. du will be itself 5 e to the negative x, but in this case we need a negative, and dx. And of course the derivative of 3 is 0 because the derivative of a constant is 0. And solving for the exponential factor e to the negative x dx equals to negative 1/5 du. So I think we are ready to go about the substitution. Alright. So we're gonna give, this is gonna give us the integral of negative 1/5 du over u, and again this is just going to be an ln rule. Alright, so let's see, what do we have? So that's a negative 1/5 ln of absolute value of u plus c, which is negative 1/5 ln absolute value of 5 e to the negative 3, oh not the negative 3, negative x plus 3 plus c. Alright, so another U substitution that led to an ln, but of course in this case it involved to use a different algebraic technique in order to have that integral U substitution ready. Let's see, what else do we have in here? Let's have a look at letter C. So letter C involves a trigonometric function, tangent squared of 2x, and this is supposed to be dx actually, for whatever reason. There's a little typo, dx. Alright, so let's see. Number one, we don't have a formula to integrate tangent squared. Well, yes, technically there is one, but that will come up later when we cover the methods more in depth. Alright, so let's try something right here. So let me rewrite. Okay, you don't have to write this actually, or if you want, that's fine. So this is the same as saying the integral of tangent 2x squared dx, where u equals tangent 2x, and what's the derivative of tangent? Secant squared, so that's a secant squared to x times the derivative, which is 2 dx. But there is a problem here. The problem here is that we don't have that factor of secant squared, so we can use it to stand the du part of the setup. So this is not going to be the way for this one. Alright, so instead let's use trigonometric identity. So in this case there's a trigonometric identity that involves tangent. So let me write it down. 1 plus tangent squared equals secant squared. Alright, well in this case we need to solve this for tangent. So tangent, that's secant squared minus 1. And well, in this case I'm using the generic version of the formula, the one that involves tangent, but of course theta. That theta can be anything, can be another Greek letter, alpha, beta, gamma, your favorite letter, or your favorite algebraic expression like x cubed, or in this particular case a 2x. Alright, so let's replace using that instead. So that's secant squared 2x minus 1. Split this into two integrals. And well, in this case, there's actually a formula to integrate secant squared, isn't it? What's the integral of secant squared? Tangent. Well, in this case, so just a quick comment on this one. I'm just going to go with the result, tangent 1/2 tangent to x. Technically, there is a mini U substitution that you could have shown over here, but I mean, it's only a number. For something this small, you're good to go and just go straight to the final result. But when it's something more elaborate, more composite, it's important to show the U like I did in the previous example, you know, like that 5 e to the negative x plus 3. Well, that one was, yes, it's still doable in your head, but for something more elaborate, show it. But for something this simple, it's fine to just go to the next step. All right. Okay, let's look at the next one. What do we have? Letter D, the integral of x squared divided by x plus 4. All right. Let's see. That's the integral of x squared over x plus x squared over 4 equals the integral of x dx plus the integral of x squared over, or dx times 1/4. Okay. Let's talk about this one. Does that look like legitimate? No, why not, Adrian?
Separate the denominator.
I'm separating the denominator in this case. Is that correct? We can't do that. All right, so yes, and that's and the reason why I'm doing this, it's because that's a very, very common mistake on quizzes, exams, and even on the homework. You know, you're working on a long problem, on a problem that already took you 10 minutes to do, and then at the end, on the last couple steps, you do this, the whole problem is wrong, you have to do it again, right? So it's important to discuss this kind of error. So what should we do in this case? Okay, someone else besides Adrian. Anna? Polynomial long division. Well, we do polynomial long division in this case because the degree of the numerator is either the same or higher than that in the denominator, all right? So, of course, let's go ahead and do that. Okay, let me take a little side trip here. Let's go ahead and do the polynomial long division. X plus 4. It's the divisor, and I'm going to have x squared. But notice in this case for the x squared, we have in a way, you know, missing terms, right? So let's summon those terms, have them a 0x and a 0. And usually you will see me doing this very, very often, and this is very useful because when we do the polynomial long division, that helps us have everything organized by power, because sometimes a power is missing and then you combine squares with cubics and fourths with sevenths, and well, that becomes a little bit messy. But having all this by power, you'll see how it works. So the number one step to do polynomial long division, what we do is divide the leading term on the dividend and by the leading term of the divisor. So in this case, what's x squared over x? X. Put that x on top of x that matches the same power. Again, that's for organization purposes. So all right. So x times x, that's going to give us x squared. But I'm going to change the sign over here. And x times 4, that's for x, and I'm going to change the sign of it as well. Why do we always change the sign? Okay, let's go back to the numerical division. 17 over 3, for example. How many times does the 3 go into 17?
5.
Is that 5? So 5 times 3, that's 15. And then subtract, right? And the remainder is 2. So what do we have? A positive times a positive. But what we do is change the sign because we're subtracting that quantity that we get. All right? Other ways to express is to put parentheses and then spend another step distributing that negative. That's most likely the way you learned it before in intermediate algebra. That's the way I teach it both ways actually, but I think it's good to just change the sign. That way we don't have to erase and write and distribute, you know. So let's see. So let's cancel x squared with x squared, and 0x minus 4x, that's negative 4x. And let's drop the next term. I know it's just a 0, it's really nothing, but again, that's for organization purposes. And in this case, because the new polynomial that we have here, it's still the same degree as the divisor, we need to do a second iteration of the division. So we need to divide negative 4x by x. What is that going to be? Negative 4. Negative 4 times x, that's negative 4x. But what do? Don't we change the sign? And negative 4 times 4, that's negative 16. That changes to positive 16. All right? So cancel, and that's a remainder of 16. All right, so how do we express our final answer? Well, in the same way that we did the 17 over 3, that's a 5, 15, 2. We express this as a 5 over 2/3. That is quotient plus remainder over the divisor. It's the same way when we talk about polynomials. All right? So let's see. The integral of x minus 4 plus 16 over x plus 4. And let's split this into 3 integrals. It would be more convenient. The integral of x dx minus 4 times the integral of dx plus 16 times the integral of dx over x plus 4. Well, the integral of x, the integral of 4, that's just regular general power rule. That's x squared over 2 minus 4x. And in this case, well, the integral of dx over x plus 4, this is another one for which you don't need to show me the U substitution, because the derivative of x plus 4 is just 1, so no need to show that one. So you can go straight to 16 ln of x plus 4. And I made a mistake on purpose to see if you can catch it. What's the mistake I did here? Absolute value, right? Is x plus 4 always positive? No, right? So in this case, we need the correct notation for this one. We need absolute value bars, all right? And that's going to nail it for letter D, all right? Let's see, let's have a look at another one. What do we have for letter E? Oh, letter E, oh, pretty interesting. Let's see. So the integral 1 plus e to the t, the whole quantity squared divided by e to the 4t. All right. Any ideas on what to do first before we can do this problem? Distribute, expand the binomial. And of course, there's a couple of ways to expand the binomial. Number one, if you're used to write it as a product of the two and FOIL it, that's fine. However, that could be time consuming. You can just use the binomial formula, the binomial square formula. So in this case, well, so that's the integral of 1 squared plus 2 times 1 times e to the t plus e to the t quantity squared. The whole thing divided by e to the 4t dt. All right? And then let's simplify the parentheses and everything. So that's the integral of 1 plus 2 e to the t plus e to the 2t. All right? Be careful with that one, because another common mistake to the t squared. It's to write it as e to the t squared. Be careful with this one. Okay? And that with respect t. So in this case, well, what would be next in order to keep going with this integral? Separate the numerator, right? Separate the numerator. So that's the integral of 1 over e to the 4t. Let's leave it like this for now. Plus 2 times e to the t over e to the 4t plus e to the 2t divided by e to the 4t with respect t. Alright? So from here we can just use the properties of exponentials. Or rather laws of exponents to simplify this one. So I'm going to have this e to the 4t to the numerator with negative exponent. And then plus 2 e to the t minus 4t. What is that going to give us? E to the 2t, so t, that's going to give us negative 3t. And what about 2t minus 4t? And this one can just be integrated. Again, no need to show me the U substitution. I think writing the U substitution for each of these ones, it's going to take longer than it takes to do that on our head. So that's fine. So that's negative 1/4 e to the negative 4t plus 2 times e to the negative 3t. Wait, no. That was just... So that's plus 2 e to the negative 3t times negative 1/3 and plus negative 1/2 e to the negative 2 plus c. 2t actually. And let's clean up the coefficients, the signs. That's a negative 1/4 e to the negative 4t minus 2/3 e to the negative 3t minus 1/2 e to the negative 2t plus c. And that's final answer. Any questions about this one in particular? Yes.
So when you enter into negative 4t,
Mm-hmm.
it wouldn't be like u to the negative 3t, no, right?
Over this one right here?
Oh no, after, because I'm kind of confused on how we integrating into the negative 4t.
Oh, you mean each individually?
Yeah.
So in this case, well, yeah, that's a good question. So whenever we have an integral of the form e to the a t dt, a can be any coefficient, positive or negative. So basically our u equals a t du, just a du, and du, I mean dt rather, and dt equals 1 over a du. Alright, so that's why in the end that's 1 over a integral of e to the u du. So the integral of du, it's always itself just the same as the derivative. So ultimately we divide by the number that multiplies that variable t. But this one, this kind of well, it's not necessarily a shortcut. This one works only when our power of the variable is 1. For higher powers like t squared, t cubed, well, in that case we need to show the u du part of the problem. All right? You're welcome. All right. So let's see, letter F. All right. What about letter F? Any ideas on what to do before we can do anything on letter F? Complete the square, yes, sounds good. And the reason why we will have to complete the square is because I claimed U substitution is not going to work. And you'll see why, because if u equals 1 minus 4x minus x squared, the derivative du will be negative 4 minus 2x dx. Do you see that in the numerator multiplying with the dx? So that's where the issue is. So we need to try something else. So let's go ahead and complete the square. Alright, I'm going to write this polynomial inside of the radical outside over here. I'm going to start with the leading term. Okay, and to complete the square, we need to make sure that the leading coefficient is a 1. Well, in this case, we have a negative sign multiplying it. So let's factor it out. X squared plus 4x plus 1. Alright? Well, in this case, we need to introduce that magical number that completes the square. Alright, how do we introduce it? Well, negative x squared plus 4x plus number plus 1. But I mean, if we add that term, be careful here, because if I add whatever number, that number is being multiplied by a negative. So what do we need in order to keep the integrity of the original expression then? Minus the number. So yes, I mean that looks, because they're opposite visually, but be careful, because this plus will become a minus with the negative sign outside. So what should we do in this case? Plus, alright? Alright. So let's see, what will that magical number be? Well, so 4 over 2 quantity squared, which is 2 squared, which is 4. 4 and 4. That expression inside of parentheses, x squared plus 4x plus 4, just right at the moment you add that magical number, that turns into a perfect square trinomial that can be just factored the following way. Minus x plus 2 squared, that is the square root of the first term, the sine of the middle term, the square root of the third term. The whole term, both terms actually squared as a binomial, and 1 plus 4 equals to 5. Alright. So I think we can, not equals, it's actually plus 5. I'm going to write it in the reverse order. 5 minus x plus 2 quantity squared. And from here, let's go back to the original problem, that is the integral. So I'm going to rewrite the integral of the square root in the denominator, 5 minus x plus 2 squared dx. Alright, and let's have a look at that integral. Any ideas on which formula or method? Well, sure, a baby U substitution is going to work. But what else? Yeah. The arcsine rule. Alright, that's the arcsine rule. Okay, so number one, let's set up the u du part. So in this case, u equals x plus 2 du, which is simply the x, which is great. And well, in this case, a, which is the quantity whose square is the number 5. What's that quantity? Square root of 5. Great. All right, let's do the u substitution. So that's going to be the integral of the square root of 5 squared minus u squared du. And in this case, well, this is simply the arcsine of That's x plus 2 over square root of 5 plus c. And I don't think you need to rationalize this denominator. I believe this will be fine. So, questions about this one? Yes.
Don't you have to multiply by 1 over a, so 1 over squared is 5?
Good question. That is true only for the arctangent one.
Okay.
So let me go back to that one. No, I don't think I have those notes here. No, because those I did it on paper. That was the first day topic. So, and let's do one last one to before we go to a break. So let's see. The integral of cosecant x. Well, of course, I think there's a formula that you have memorized for cosecant x, which I believe, well, there's actually two versions of it. I'm going to show you both versions later. But I mean, how do we derive a formula to integrate cosecant x? In this case, we need to, I know, this is just weird. This one just works. So I'm going to multiply numerator by cosecant x plus cotangent x and divide by itself. And that with respect x. Alright? Well, the reason why we do that is because, well, it just works. Alright? So let's multiply this across. Let's simplify a little bit. Well, there's not much to simplify. So in this case, so that's cosecant times cosecant. That's going to give us, well, the integral of cosecant squared x plus cosecant times cotangent. And in the denominator, simply cosecant plus cotangent. Alright, so let's have a look at this problem. Well, so it looks like the numerator is a bit more complicated than the quantity in the denominator. That could be the case that it is indeed the derivative of what we would set as a u, which is the denominator. We'll see. So let's see if that's going to work. So u equals cosecant plus cotangent. The derivative of cosecant. What's the derivative of cosecant? Cosecant cotangent. And what's the derivative of cotangent? Cosecant squared. Actually, it's negative, right? Recall that the derivatives of all the co-functions like cosine, cotangent, cosecant, they're all negative, right? So that's a good pattern to recognize when coming up with those derivatives. And the derivative of cotangent, which is cosecant squared, that is also a negative. And of course, if you compare this with what we have on the integral, multiplying with the dx, it's almost the same except for those negatives. Let me take those outside. And I'm going to write cosecant squared plus cosecant cotangent. And well, this is the same as saying, oh, actually, du. So cosecant squared plus cotangent, or rather cosecant cotangent, equals negative du. Alright? So let's go back to the integral right here. So this will do it for this. That's the u du part. And well, so that's negative. The integral du over u, and the negative outside goes just so I don't leave it inside of the integrand. Either way, that's fine. So that's a negative ln of u plus c. And if we back substitute for u, that's negative ln of cosecant x plus cotangent plus c. And that's one of the forms that you learn in Calc 1 in order to integrate the cosecant function. Another one that you may have learned is this one. Positive, but with a negative inside. That's the other version, so two versions. How do we do that? Well, that negative goes as a power here, send it to the denominator, and multiply by the conjugate, and then eventually you should get this. Okay, we don't have to do all that, that's fine. The idea was to multiply, to use the conjugate, well, in a way the conjugate, the trigonometric conjugate, so we can derive this formula right. Alright, so actually this completes the section. That's all we have for the section. So let's take a 10-minute break.